Luke, I am your father. Submit to the dark side. No, you're not my father. You're not my father. Who's your father? I don't know. I never had a father. Okay, well, hey, good always prevails. What do you know? Let's go through uh some of the theorems and see how we could apply those to do good, not evil with series and get serious about it on May the 4th as well. So this is for Luke, but it's also for everybody else that happened to show up to class today because we didn't really give examples of the theorem. So I want to do that for you now. So here we go. Got to find the pen that writes on this stuff. All right, but we had a couple of theorems. Theorems are proven facts, so we have some theorems. If we have one of the theorems said, hey, if the infinite series, and sometimes in my other videos I end up saying sequence, but the sequence would be like A1, A2, A3. The series is adding up those terms, and the series of partial sums. So we do have a sequence of partial sums is different than the series. So this is an infinite series. So forgive me when I do that wrong. But if I have the infinite series of the sequence a sub n, and we're adding up all those terms. But anyway, if this converges, and if the infinite series n equals 1 to infinity of b sub n converges. So basically the sum is going to be a specific limit. Then the sigma of the sum n equals 1 to infinity of a sub n plus b sub n. Also, if I add them up as I go, each part, this is also gonna converge. So this converges as well. And what happens is the book uses S and T. So if this exists, and if this infinite series equals S and this infinite series equals T, some specific real number, then this is going to converge to what? To S plus T. So the sigma of the sum is the sum of the sigmas when they converge, and that's a pretty obvious thing. But I could also do like a minus sign. So the sigma of the difference is the difference of the sigmas. And so this would also converge to, actually this other one really should be blue, S plus T, but the minus sign, so the blue one, to add it would be S plus T. And then the red one, since I did that, would converge also, and it'd converge to S minus T. So the other way is, how can we use this? What else do we have? If we have this one, if this diverges and does not approach a specific real number value, so if this diverges, then what do we know about either one of these? This would also, the sigma of the sum or the sigma of the difference would also diverge. So let's, for example, if we have, let's say this diverges and this infinite sum goes to infinity. So we're just adding up the sigma n equals 1 to infinity of n. Well, we know that keeps getting bigger and bigger and bigger because you're going to add bigger numbers, so that goes to infinity. Well, if you add any other sequence, whether it converges or not, if you add t, some specific real number, to infinity, it's going to be infinity. And similarly, if you subtract infinity minus some specific number, is still going to be infinity. Okay, so we have that. Now, similarly, what if this other one diverges and the first one converges? This is still the sigma of the sum, or the sigma of the difference, is also going to diverge. So we do need, if we have a sum here or a difference, we do need them both to converge. So let's just look. I didn't really look at examples of that, but let's look at a couple examples potentially here, and I'll just try and come up with something off of the top of my head. But if I have the sum n equals 1 to infinity of 1 over n minus 1 over n squared. And I have that, and I say, what's this gonna go to? Basically, we can say this is equal to sum n equals 1 to infinity of 1 over n minus the sum n equals 1 to infinity of 1 over n squared. Okay, and what we know here is that this one actually goes to infinity, right? This goes to infinity, and and then the question would be, as long as it's not infinity minus infinity, which is indeterminate, if I have 1 over n squared, then that is, let's say that this ends up approaching a specific value, which I don't know if I can pull that out real quick or not. But anyway, so this is, well, how about this? What if I change it and I say, hey, this is 1 over 2 to the nth power. Now this is if I have 2 to the nth power, that's different, because now this is a geometric sequence. This is 1/2 plus 1/4 plus 1/8 plus 1/16, etc. So this converges here. But since this one diverges because it's harmonic, right? And we have a theorem that the harmonic series diverges. Since this one diverges, then this right here would actually be, this would actually diverge as a series. Okay, so that's one way we can use that. So basically, if we have the sigma of the sum, we need both parts to converge for it to be convergent. So anyway, so we can use some of the things that we know. We also have a few other things. Let's look at another example. What if I have the sum, not an example, but a theorem. Let's look at a theorem. If I have sigma n equals 1 to infinity of k times a sub n, well, this is going to be equivalent to k times the sum n equals 1 to infinity of a sub n. And that's just the distributive law. This is nothing more than the distributive law on infinitely many terms, right? So I can pull that k out in front by multiplication. So we said this when we had the upper limit, we had I equals 1 to n on this. We said the sigma of a constant times the function is the constant times the sigma of the function. Of course, the function is a sub n, which is a sequence. A sequence is a type of function, because I could call a sub n, we could call that f of n if we want, where the domain is the natural numbers. But anyway, so this is true here. We can pull that k out in front, and so that's good to know. So when is this going to converge? If this converges, if we have the series n equals 1 to infinity of a sub n being convergent, then this is going to be convergent as well. Then that would imply that this converges here, and what's it going to converge to? If this converges to, I think we said s for a specific limit, then this one would converge to k times s, for the simple reason that, we can pull that k out in front and go from there. So the distributive law ends up proving this, but k times s would be this. Of course, if we don't have that this series converges, let's say it diverges, then what? If I take any constant number, real number, times a sub n in there, then this one is also going to be divergent. So we can utilize that theorem that way as well. So let's try and look at see if we can come up with a real quick example here. What if I have sigma n equals 1 to infinity of 1 over 5n? Okay, so if we have something like that, we might say, well, is that convergent, divergent? If it converges, what does it converge to, etc.? Well, what I could do is I could rewrite this as 1/5 times 1 over n, right? So that'd be equivalent to sigma I equals 1 to n equals 1 to infinity, sorry, of this thing, right? And then what can I do with that 1/5? I can pull that sucker out front, and if I do that, I'm going to get 1/5 n equals 1 to infinity of 1 over n. So now, since it's that, the sigma of a constant times the function is the constant times the sigma of the function. Basically, what can I say now? Well, I can say that this is actually the harmonic series, right? And by theorem or proof, this is divergent, so this diverges. And so since the harmonic series diverges and this diverges, that means it does not approach a specific sum as n goes to infinity, which means that if you take it times 1/5, it won't either. So this thing up here, that implies coming back up here that the sigma n equals 1 to infinity of 1 over 5n also diverges. Okay, so a couple quick, easy examples on how to do that. So now let's look at one more example that maybe gets a little bit more involved. But if I have the sum n equals 1 to infinity of something like 1 over 5n plus 1 over 5 to the nth power. So if I have something like that. Well, once again, since I have this, I can sigma the sum is the sum of the sigmas. So I can write that as sum n equals 1 to infinity of 1 over 5n plus sum n equals 1 to infinity of 1 over 5 to the n. Now, a couple things to note here. Let's look at this one first. This is actually a geometric sequence where the value of r is r equals 1/5, and that's less than 1. So we can notice that this is a geometric sequence there, and this actually converges to a specific limit. We can call it anything you want, but let's say that goes to, for the second one, we were using t a lot, that's some specific number t, but it converges. But then, of course, what do we know? We know that the first one here, this, if I take that 1/5 out front, then it's 1/5 sigma 1 to infinity of 1 over n, but that's the harmonic series. This is divergent. So we have a divergent series plus a convergent series, which is similar to the previous example. But in this case, this left side doesn't approach, this left series doesn't approach any specific value. And so we have a divergent series plus a convergent series. So that means that this entire one up here, sorry, that should have been in blue, actually is divergent. Okay, so we didn't need the one on the right, but the one on the left sufficed in this case. But anyway, like I said, if we end up, if the first one goes to infinity and the second one goes to infinity and we have a minus sign in between, we got to be a little bit careful there too, because which infinity is bigger, or are they approaching infinity at the same pace, et cetera, et cetera, et cetera. So, you know, you can't just find one being infinity and think that necessarily you're done either. But those are a couple of theorems there that we had, and let's see what else, if I did anything else on those today. I don't see that I did, but those are kind of the main ones there too. And then of course, you know, geometric series. You know, if we have, you know, just remember this theorem here for a geometric series. This is one we can use too. So if we have sigma 1 to infinity of a times r to the n minus 1 power, where a is some specific number, but basically this is just a series where the value of each term, the next successive term here, you're multiplying by the ratio r to get to the next successive term. But anyway, this converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. Okay, so we had that as well, you know, things of that nature. So anyway, couple of things. And so the question is, what did I have? I had 1 over 5 to the n power. All right, and we said, hey, that's a geometric series, which means that this would be a geometric sequence. Well, what would that equal? That would equal 1/5 for the first one, and then 1/25, and then 1 over 125. 5 cubed is 125, etc. And so the way we get to the next successive term is by multiplying by 1/5. To get there. So I'm multiplying by a fixed number. So the next one, multiplying by 1/5 would be 1 over 625, right? Would be the next successive term there. So I'm multiplying each one by 1/5. So in this case, the ratio R is the same as A, the value of the first term. And so in this case, we have 1/5 times 1/5 to the n minus 1 power. And of course, this is 1/5 to the first power times 1/5 to the n minus 1. We add exponents, and this is equivalent to 1/5 quantity to the nth power, and which is also equivalent to 1 over 5 to the n power. So sometimes you got to let your eyes recognize, hey, this thing, 1 over 5 to the nth power, is actually a geometric sequence, and trying to write it like this can be a little bit awkward when they're the same. Things of that nature. Something that might be a little more obvious, what if I had sum n equals 1 to infinity, let's just do it, of pi times, let's use a ratio, times 1/2 to the n power. Well, this isn't quite the same here, because now I have an n there, but I wanted an n minus 1. Well, how could I rewrite that? I could say, well, this is equivalent to sum n equals 1 to infinity. I'll leave the pi in there for now. That's a constant we could pull out. But anyway, if I take it times 1/2, and then what would be left? Times 1/2 to the n minus 1 power. I could do something like that, right? And then, of course, what can I do now? 1/2 times pi can come out front, so this is equivalent to pi over 2 times the sum, n equals 1 to infinity, of 1/2 to the n minus 1 power. Okay, now remember, so in this case, this is also a geometric sequence, right? Where we have, if I write that sequence out, 1/2 to the n minus 1 power, and I write out the elements, if I plug in n equals 1, that's 1/2 to the 0, which is 1. And then 1/2, if I plug in 2, it'd be 1/2 to the first, and then 1/2 to the second, which is 1/4, 1/8, etc. And it keeps going, right, on that sequence of terms here. So what's A? The question is, what's A? A is 1, and what's the ratio? The ratio R is 1/2. And of course, I could write 1 times 1/2 to the n minus 1. So this is A. A is 1, and R is 1/2, right? So basically, what does that converge to? We said since the absolute value of 1/2 is less than 1, so I do know that this thing converges, but then that theorem also says what it converges to. It converges to A divided by 1 minus R. That's what it converges to. So in this case, what's this converge to is going to converge to A is 1 divided by 1 minus 1/2, or 1 divided by 1/2. So this converges to 2. So this equals 2 here. That's what that converges to. So this is going to equal pi over 2 times 2, which of course the 2's cancel. And that says that, hey, the limit of this series that I gave you here is convergent, and it actually converges to an infinite sum of pi. So if you add up all of these terms as n equals 1 to infinity, it ends up equaling pi. So that's a couple of ways that we can use the force and kick some tail on some bad guys. And there are bad girls out there too, don't forget that. But anyway, and use the force for good, not evil. So I will talk to you later on Cinco de Mayo.